Another thing you may have been wondering is how possibly could integrating to infinity be relevant or useful for anything? What's actually pretty interesting is it's actually quite useful in a lot of different areas of math, statistics, and physics. Integrating to infinity actually is super useful in a lot of astronomy and a lot of other calculations, but to name a few example. In math, it's also quite useful for various transforms, like what are called Fourier transforms, Laplace transforms. I think you have a homework problem on on a little bit of that. And certain functions are even defined as integrals to infinity, like Fresnel integrals or gamma functions, and so on. So, anyways, knowing how to integrate to infinity is quite useful. And actually integrating across all the reals. So say we wanted to know what is the integral from minus infinity to infinity of a function, or literally the area under the entire curve, assuming it is continuous on the reals. Well, basically you would need to split it into two parts, because if you like, in terms of taking out the limit, technically you could think about, what if I took the limit as t approaches infinity from minus t to t of the function. But it's wiser just to split it in some position in order to figure it out, because algebraically speaking, if you integrate from minus t to t, depending on what function it is, it could cancel and give you a result that is not correct. But basically, it does not actually matter where you split it, and I believe this page number may be incorrect. I don't remember if I've forgot to update it for the new version of our textbook. But regardless, let's peek at an example. So say we wanted to know what is the antiderivative of 1 over 1 plus x squared from minus infinity to infinity. Or, the graph of the function is right here. It's a function which sort of resembles what's a bell curve. It's actually not the same graph, but has some similarities. And why such functions can be useful is a probability density function is a function whose, by definition, the integral underneath the entire curve from minus infinity to infinity must be equal to 1. An idea we might return back to when we get into various applications in the next couple weeks, but no guarantee we'll have time to get into that. But such an integral would be something we may need to solve in statistics, or consider at the very least. But essentially the idea is, well, what's the area underneath this curve forever? And, obviously if we integrate from -4 to 4, it gives us sort of an estimate to begin with. But again, the question is, does this converge or does it diverge? And one simple way to set this up is, well, I could split this integral into two parts. The integral from minus infinity to 0 of 1 over 1 plus x squared with respect to x, plus the integral from 0 to infinity of 1 over 1 plus x squared. And the reason I would split it up at 0, well, you could split it up anywhere, but it is actually an even function, which actually means that these two amounts of area should be equal. And technically, we could just double it in order to solve the total area. But let's just leave them separated and solve them separately. But essentially, we have two infinities, and we could extract those as separate limits or as a singular limit. Say the limit as t approaches infinity of I'll just write this in brackets, the integral from -t to 0 of 1 over 1 plus x squared dx, plus the integral from 0 to t of 1 over 1 plus x squared with respect to x. A little bit small. But basically this integral, if we did not know what this was, we could use trigonometric substitution to solve it. But as this is a formula we've already seen in the past few weeks, the antiderivative of 1 over 1 plus x squared is just the arctangent function. So essentially, if I'm trying to solve these integrals, well, next after extracting the limit, and another point of emphasis is, if you're doing an integral from minus infinity to positive infinity, you need to break it into two integrals first, and then extract the limit from each, or as I did it as a singular t. And then this, basically each of these antiderivatives, well, this would be the arctangent function evaluated from 0 to minus t, and the next one would be plus the arctangent function evaluated from 0 to t. And plugging in our boundaries, of course, here all we'd be left with is, well, the arctangent of 0 minus the arctangent of negative t plus the arctangent of positive t minus the arctangent of 0. And now, even if you didn't know what the arctangent of 0 was, notice that there's a cancellation because you have both the arctangent of 0 here and minus the arctangent of 0 here, and it would cancel out anyways. Another reason you might be thinking, well, why did I need to separate them to begin with? But again, you know, let's move on. So what was my point? I don't even remember. But basically the arctangent of 0 is 0 anyway. So of course 0 minus 0 is 0, but those all cancel at the end of the day. And this is a weird looking parentheses. Let me fix that. And now what I need to know is, well, what's the limit as t approaches minus infinity of the arctangent of t? So kind of considering each of these, and the other reason why I put the arctangent graph on your packet is because the arctangent is a function where you may not know the limit towards infinity, but the arctangent is the inverse of a normal tangent, which, if you remember the general shape of tangent function, it looks kind of like, you know, your noodly guy, wacky waving arm, flailing arm guy. And it has vertical asymptotes at minus pi over 2 and pi over 2. And technically the tangent function is periodic, and actually is periodic based on pi. It repeats itself every 180 degrees. But the arctangent, all inverse functions can only have to be of one-to-one functions. So basically it's just one interval of the function, which is by definition the arctangent, and it looks exactly like this. But it's the inverse if you flip it across the line y equal x. You know, it just looks like a kind of reversed mirrored tangent, just one interval. And anyways, the point is, if you were to plug in infinity, or if you plug in an arbitrarily large number, arctangent will head towards pi over 2 on the right and negative pi over 2 on the left. So in this one, we have negative arctangent of as what will happen towards minus infinity. And towards minus infinity, what we'd have is minus pi over 2. So what I'm going to have, I'll just write it using the limit notation. This guy will trend towards negative pi over 2. And then the limit of the arctangent of t as t approaches positive infinity will head towards positive pi over 2. And so what I end up with is, well, this would be a double negative pi over 2. Plus a pi over 2. And of course, double negative pi over 2 is positive. And what I just have is pi over 2 plus pi over 2, and half plus a half is a whole pi. And so what we end up with is the area underneath this particular function, which is, again, a pretty useful mathematical function, is pi, which is kind of a cool little mini factoid to say. So if I'm kind of imagining this particular function, if I integrate it literally forever, continuing from minus infinity to infinity, that area magically adds up to pi, or the area of a circle with a radius of 1, interestingly enough. And there's a lot of reasons and connections in math about why that's kind of neat and interesting. But for now, we will leave it at that. And in the next video, we'll get into what is an improper integral of type 2. Those are a little bit less easy to identify because the type 1 improper integral has an infinity. It's a little weird, so automatically you kind of recognize this is improper. Where type 2, we'll talk about how to figure out when that will happen.